Excellent. Donc, bonjour tout le monde. Bienvenue à notre premier colloque des sciences mathématiques du Québec de cette année. Welcome everyone to our first colloque des sciences mathématiques du Québec of the year. It gives me great pleasure to introduce today's speaker, Charlotte Chan, professor at the University of Michigan, also someone that I know from when we were both at the University of Michigan as graduate students. So you can imagine it's very nice for me to see a friend here today to tell us about some great mathematics. To tell you a bit about Charlotte Chan, her research is in representation theory. Parts of it are in number theory with interesting applications to algebraic geometry. She's quite a talented mathematician with diverse interests. After her time at Michigan, she went and did postdocs at MIT and at Princeton before being hired back at the University of Michigan. She's also been the recipient of the Sloan Fellowship in 2022, which is one of the most prestigious awards for young mathematicians out there. So truly someone excellent at mathematics. Inside joke. And well, no, I mean, it's not such a subtle joke. Anyway, so without further ado, we're very happy to have Charlotte here today. I actually didn't write down the title of your talk. Was it something about positive Deligne?
Yeah, perverse sheaves and representation p-adic groups. Actually, I don't remember what title I gave, but that's what I wrote down on my paper.
Right. Well, without further ado, take it away, Charlotte.
Thank you so much for the nice introduction, and thank you so much for the invitation and the opportunity to be here. It's really an honor and a pleasure. I like Montreal very much. Yeah, so yesterday I gave a talk as well. I don't know whether everyone in this audience was there, and of course it's not a prerequisite for this talk. But sometimes I will refer to the yesterday's talk just to connect the material from today and the material from yesterday. Yeah, so they are complementary, but they have some overlapping themes. Okay, so maybe I should just write down. Okay, so the starting object for me is a representation of a group G, and this means that one has a vector space, which for me, I think actually maybe the whole talk, my vector space will be will have coefficients over the complex numbers. And what is a representation? It's some vector space where the group acts on the vector space, and this thing respects the linear structure coming from the C linear structure of V. And a very fundamental idea in representation theory is the idea that one way to construct representations of G is find some subgroups of G, let's say H, and find some representations of this smaller and therefore hope easier group, and then average this action out so that you can build up a bigger group action on a bigger vector space. So in some sense, this is a bit like this goes to some number of copies of W, where on each W we have this H action, and then amongst these there's kind of a permutation action of G mod H. Okay, so this isn't so precise, but this is some picture of how to think about this concept, and this concept is called induction. And in some sense, induction is like one of the only ways that, like, no matter what kind of groups you look at, all representation theorists think about induction. I guess a counterpart to that is that depending on what kinds of G you study, the tools in representation theory at your disposal differ. So for example, so maybe I put this here. Tools in representation theory depend on what G you like most. So as an example of something that I won't talk about, if you take, does this go? Okay, this goes up. Okay. If you take G to be Sn, symmetric group, then one knows that the irreducible representations of this group are parameterized by partitions. Okay, this is close enough. Partitions of n, and partitions of n is some list of some number, some integers, where the sum is equal to n. So these are positive integers. And so in this world, one of the tools at your disposal is combinatorics that come from this parameterizing data over here. There are other ways to study representations of Sn as well. But I won't talk about representations of Sn, so I won't go into it. So in this talk, the kinds of G that I'll be most interested in are groups that look like GL2 of Q. Might as well do here. And this means all 2x2 matrices with coefficients in FP and invertible. So determinant is non-zero. So AD minus BC is required to be non-zero. And in this context, we have a special kind of induction that's particularly important. And this is called parabolic induction. And so let me write down for you what parabolic induction means in the example of GL2FP. I'm going to take B to be upper triangular matrices sitting inside my G. And this B has a natural surjection to the diagonal elements, which looks like this, by just forgetting the top right corner. So given, let me define it here. So given a group homomorphism from T of FP, so I just write T, T to C star, one can consider I'll call it p-ind. The P stands for parabolic induction. To be the induction, in other words, this process from going from W to V, the induction from B to G of how should I say, which I do this one first and then followed by like this. Okay, so I have called this for projection. Okay. Okay, so whatever this object is, it's I wrote in my notes the definition, but I'm a bit wondering whether I want to do that. Okay. Yeah, let's do it. Let's do it. So one way to view this is it's the space of all functions from G to C satisfying the following transformation property. For any element G inside your group G, which is my GL2, and any element B inside my BREL, which is my upper triangular matrices, this thing is equal to theta projection of B multiplied by the original. So this is a space of some functions whose values are in C. This is a complex vector space. And its dimension is simply given by the number given by number of things inside G divided by number of things inside V. And that's something explicit that we can compute. We can do it if you like. Number of things inside GL2FP is p squared minus 1, p squared minus p. And number of things inside B is p minus 1 squared times p. And so I think if you compute this out, you get p plus 1. Okay. Okay. So this is an example of a representation. It is a complex vector space, and it comes with a group action. And what's the group action? The group action is given by precomposition. So when you have a representation, you have an action of G on this V. Actually, this kind of data is the same as giving a group homomorphism from G to GL of your vector space. So if in this case I have size p minus p plus 1, and so this data simply gives me a way of mapping any 2 by 2 matrix here to a p plus 1 by p plus 1 matrix with coefficients in C. So now, remarkable fact. Which I was floored by when I learned this as a student, is that this map from G to GL p plus 1 has a lot of structure. And the fact that reflects this structure is the following thing. If you consider the composition, G goes to GL p plus 1, then goes to C by taking trace. So remember, trace just means to sum the diagonal entries. This thing remembers at least the isomorphism class of the representation. So why you should think that this means that representations have a lot of structure is that obviously this is not true matrix by matrix. If I say I have 2 matrices like A and B, they have the same trace, or okay, just one. I have a matrix, it has trace 3. It has size 15 by 15. There's a 0% chance that you can predict which one I'm thinking of. Yes? Yeah. But that's not the case for a representation. If you have a representation, you only remember the trace, you recover the whole thing to isomers. Okay. So this is something really remarkable. Okay. So this means that the studying the representation theory of G is the same as studying certain functions from G to C. Some nice functions here. Okay, and so actually, for the rest of the talk, I'll forget about the representation theory question, and I'll just study these nice functions, G to C. Okay. Okay. So when you take a representation theory class, you'll learn how to calculate this corresponding composition. This is called the character of a representation. And let me tell you what the character of that representation is. And I'll write it as chi sub theta. And what we know is that we're looking for something that takes in a 2 by 2 matrix and spits out a number. And the number that it spits out is some average. I don't want to write it. Okay, I can write it in this way. That's the formula. Yeah. So another way to write this. What?
G is the matrix.
G is, oh yes, that's right, thank you. Another way to write this is that I'm summing over all cosets such that this happens. So remember the shape of this formula. This will come back in like 30 minutes. Okay, so before it comes back in 30 minutes in this particular way, I want to show you some specializations of this formula. Okay. Oopsies. Okay, so say I take phi theta of, let's say, A00D. Okay, and I just plug it into this formula. Then this formula says that I need to calculate all elements of GL2 that conjugate this element back into the upper triangulars. Okay, so when you do that, you'll find that there's actually not so many choices that you have. Your only choices are you do nothing or you swap A and D. Those are the only two options. And so what you find is that this is equal to theta times, theta evaluated at AD plus theta evaluated at DA. Maybe I say, for example. And so this is a particularly nice specialization. This is such a nice formula, and definitely it looks more like, it looks slightly less opaque than this one, even though this one maybe is also very nice. It's explicit. Yes, good point. Yeah. So if A is equal to D, then this matrix is central. So of course, then you just get some multiplicity in front of theta of AD. Okay. Okay, now a structural comment is that trace doesn't depend on my choice of basis, right? So in particular, that means it's invariant under conjugation. And what that translates to for the character is that conjugating by G doesn't affect this, this function. So in what just computation is essentially the value of this function and any G, this is my G, where it has distinct eigenvalues. Let's call it alpha and beta, then this is going to be theta of alpha beta plus theta of beta alpha if alpha and beta are an FQ star. So this is something that we saw yesterday. Okay, so let me fill it out over here. Why did I leave something blank here? Well, a spiel that I gave yesterday, and I'll give it again now, is how do you eigenvalues of a 2x2 matrix? Well, you write down the characteristic polynomial and you find the zeros of this. Characteristic polynomial of a 2x2 matrix is a degree 2 polynomial. And its coefficients are given by things in FQ. And so if you're trying to solve, find the roots of this degree 2 polynomial with coefficients in FQ, then at worst the roots are in FQ squared. But that's like a legit possibility. So over here, one possibility was that the roots were in FQ, but actually there's another possibility, is that if the roots are actually in FQ squared or not in FQ. Okay, so what happens in this situation? Well, we can try to say, suppose you have an ABCD where the eigenvalues are not in FQ star. Then is there any way to conjugate it into B? Well, what does B look like? B looks like a diagonal matrix, right? And all the stars are in FQ star. What are the eigenvalues of an upper triangular matrix? Well, they're just these two entries. So in other words, if your two eigenvalues are not in FQ, there's no way to conjugate this into B. That means that this indexing part is empty. So we get 0. So this is the derivation of one of the formulas that we saw in yesterday's talk. Okay. So here's a fact. And I'll call this formula star sub theta. This is also like in yesterday's talk. So the fact is that P int of theta is in fact the only representation satisfying star sub theta. So in other words, first I said you have a representation and you look at its trace, its character, and that uniquely determines the representation. Now I'm just looking at the character values on this special locus, not for all ABCD, only ABCD with distinct eigenvalues. And the assertion here is that actually already that recovers the whole representation. So you have even more symmetry than you thought. Okay. So now, of course, as mathematicians, we're trained to look at patterns. And one thing you might feel a bit unbalanced about is the fact that you have a non-zero thing here and a zero thing here. So you might, like, to balance out the universe, ask whether you can swap the roles of the zero and non-zero parts. And so, in fact, you can. There's a counterpart to star theta with the roles of the theta plus theta w part. That's how I'm calling this part, where your w is acting by swapping the alpha and beta and 0. And that's the following formula. The formula is that chi is some function where it takes in an ABCD with distinct eigenvalues, alpha and beta again, and it pops out exactly the same thing, but the roles swapped. So I'll also put a theta here, and I'll say theta now will take entries for the FQ squared part. It's 0 if alpha and beta are in FQ star. And it's theta of alpha plus theta of beta if alpha beta are not. Okay. Yeah.
And so here, this is a different theta, like there's some other traces, some other representation.
Yeah, so I haven't said anything as yet. This is so far just a function, but it's about to be the restriction of the character of a representation. So here's the fact. For GL2, this predates the. Okay, so in general, this result is due to Lusztig in the late 1970s, early 1980s. For GL2 is probably known maybe 30 years earlier than that by Green. But the counterpart to the above fact is exactly the same statement, but now for this other theta as well. So regardless, maybe I say it like this, regardless of which situation you're in. And maybe I say it like this. Maybe I say it like this. Still, there exists a unique, irreducible representation, pi, such that chi pi on the part where one has distinct eigenvalues is equal to star sub theta. So I suspect I won't be able to leave this here forever. So let me erase it. And let me draw a picture of these two facts here. So here's what we have. Okay. Okay, before I draw the picture, let me make the following comment. So how did we come up with this formula over here? We actually exhibited a representation. That came from parabolic induction. It was an easy thing to do. It's simply given by some explicit space of functions on the group. So that's but in the second fact, I'm not telling you which representation it is. I'm just telling you somewhere out there, there's a representation, and it's the only one whose character satisfies this relation. And how you should think of this is that parabolic induction is an easy process. If you can get your representation using parabolic induction, you are in good business. But those aren't the only representations of the group. There's a bunch of other ones, and for GL2, there's by doing parabolic induction, you only get half of them. So the ratio that you get from pure parabolic induction from a Borel shrinks as the group gets larger. So you should have this sense of that, kind of, there's more and more stuff that looks like this, or some mix of these two things. Something that's purely parabolic induction is actually a shrinking slice, but there's always a positive proportion. Okay, an additional fact that that I haven't told you is that for GL2 FQ, basically all irreducibles are one of these two types. So actually, let me write that down. Basically, all irreducible representations of GL2 FP fall under one of these two categories. And so for the purpose of the picture, I'll just pretend like it's actually all, but probably you should write some. So here's the setup that we've discussed over on the right-hand side, which is that characters of, okay, maybe I read it here, some, most, I think I can safely write most irreps. There's a map from this to some functions on this the part of G with distinct eigenvalues, which is called the regular semisimple part. And this is just given by restriction. So, and this function is given by star theta. And so the content of these two facts is that, in fact, there's no loss of information by going over here to this restriction. So it's actually a bijection. On the right, exactly say that this is a bijection. So you have characters of irreps, you restrict it to this thing, claim there's no loss of information. A very natural question we can ask is how do you uncover Love's law? The values of the regular semi-simple part in the same way to figure out what's happening on the boundary. How to recover chi on the part outside the regular semi-simple locus. We know it's uniquely determined. Okay, so let me first give an analogy. Suppose that instead of working with GL2FP, you were working with GL2C. Then when you take the character of a continuous representation of GL2C, you get a continuous function from GL2C to GL2C. So say you have a continuous function, GL2C to GL2C. Oh, to C. Okay, well, what's something that you can do? Well, let's say I restrict this function to the part where your 2x2 matrix has distinct eigenvalues. So now perform this process, restriction. And you get some function on GL2, C, distinct eigenvalues. What proportion of GL2C is this locus here? 100%. Yes, 100%. Okay, so this is 1% of GL2C. Well, but not all of it, yeah. Okay, so so what should we actually say? We should say that this thing here, the regular semisimple locus, is dense inside GL2C. Yeah, you have a continuous function, you restrict it to a dense locus. How do you recover the stuff you missed? Limit. Okay. So that means to recover this, the inverse map is just you take the limit. This is an analytic concept. Okay. So let's try to do it over here. I take the character of a representation, and what do I get? I get a continuous function on this discrete set. So it doesn't really have such a good meaning, right? Because what's a continuous function on a discrete set is like really any old function that you want. So we're in a bit of a bad state. But the thing is, this GL2FP kind of lives in a family where I can also take FP squared and FP cubed and so forth all the way up for arbitrarily large Q. Or in other words, it lives in a family all contained by GL2FQ, FQ bar, sorry. And in GL2FQ bar, you again have this situation where the regular semi-simple part is dense inside it. So this analytic thing of taking the limit, we want to replace with some kind of positive characteristic algebro-geometric thing on the right-hand side. And the replacement of limit is something called intermediate extension. And this comes from algebraic geometry. Okay, so this is one of the main takeaways, is that at the level of functions, we have this restriction that we can assert we improve is a bijection. But how do we recover the stuff on the boundary? Actually, we can make use of some geometry, some concept from geometry called intermediate extension. Okay, so I'll spend the rest of the talk on this concept. So putting all this together into yet another picture, we have the following thing. Ooh. So our, I don't have to rewrite it. I can do something clever board work. I will erase this part. Okay, so remember that this star theta was kind of like this. It's this kind of object that I wrote down. There's a geometric version of theta. And this geometric version of theta is something called the local system. And the geometric version of theta I will write by fancy L sub theta. And there's also a fancy L sub theta W. Okay. The fancy L stands for line. Okay. Yeah, that was supposed to be a joke because you might have thought like it stands for local system, right? Okay. Okay. So there's a passage here. So this is a passage. This local system is on GRSS. And from GRSS, what I can do is I can apply what's called intermediate extension, denoted by star and shriek and star. And I get something called a perverse sheaf. I won't tell you what a perverse sheaf is, but the important thing for us is that from like this, which has a lot of structure, actually there's a way to take a trace to get back to just a function on GL2 of FQ. So there's a way to go this way. Okay. And this is called sheaves to functions correspondence. Okay. So now we've filled in some way to go from here back up. You should ask whether this diagram commutes. So that's a theorem. Okay. Any questions up to here? Okay, so so my interest.
Since you asked, when you talk about local system on GRSS, GRSS has some structure of a variety.
Yes, yeah, it's it's an open thing inside this algebraic group G. So everything I'm a bit abusing things like this GRSS. I'm not just taking the GRS the distinct eigenvalue part of GL2FP, but really of GL2FQ bar or FP bar. So I mean, it's the complement of the vanishing of the determinant, for example. Okay, so my interest is on in p-adic groups, which is groups like GL2 of a non-Archimedean local field. And non-Archimedean local fields are things like QP or FP prime prime T. Alrighty. And so here's a picture of how let me take this situation. So what does this mean? You take the field of Laurent series with coefficients in FP, and let me draw for you a sketch of why the representation theory of GL2 with coefficients in something like this is related to the representation theory of GL2 FP. And so this comes from the following basic structure, which is that if you take Laurent series inside this Laurent series, well, definitely one of the things inside, a bunch of things inside Laurent series are power series. And the ring of power series has some natural quotients by sending powers of t to 0. So I can quotient down to FP simply by mapping t to 0. But you remember only the constant coefficient, constant term. But I can do this, I can try to remember a little bit more information and map t squared to 0, and I get FP bracket t squared. And I can keep doing this arbitrarily. So t to the r plus 1 mapping to 0 gives me a map to fp squared by t to the. This is a finite ring. It's a truncated polynomial ring. Just means you remember all polynomials up to degree r. Okay. So now this diagram also works if I put a GL2 in front here. And a GL2 here. And a GL2 here. And a GL2 here. Oh my God. GL2. And so forth. So what this diagram suggests is that if you only understand what's going on for GL2FP, you're only getting the top slice of the representation theory of this p-adic group. If you want to know more about the representation theory of p-adic groups, well, probably you want to have a pretty good understanding of what's going on over here. And to understand what's going on over here, it's really not enough to understand the bit where t is 0. I need to also understand where t squared is 0, t cubed is 0, and all the way down. Okay, so really want to understand the situation, the representation theory of GL2 of fp bracket t divided by t to the r plus 1. I'll call this g sub r. Okay. So here's the first theorem, first like not classical theorem, which is the r is positive version of the fact that I just erased. There exists a unique, irreducible representation of GR. GR is this group here, right? Like a kind of fattened GL2FP. Such that pi sub pi, when you restrict to the version of regular semisimple, which actually is a little bit different, so you have to be a little bit careful here. This thing is in fact equal to the same kind of formula that we saw for star theta. In other words, it's this kind of theta plus theta w. Okay. So that's the first thing. So we have existence is work of myself with Alexander Ivanov in 2019. Actually, maybe 2021. I think 2019 we put the paper on archive, and 2021 it was published. Uniqueness is due to joint work with Masao Oi. I think maybe 2023. Okay, so now I made this whole thing about intermediate extension, so you should ask whether that statement is also true. In other words, does Lusztig's theorem, where this diagram commutes, also hold in this setting? And the answer is yes. Moreover, intermediate extension, again, determines the values of the character of this representation on the part outside of the regular semisimple part. Regular semisimple. Okay.
Is this an induced representation, or it's
Sometimes it will. Sometimes it will be an induced like a parabolic induction, or a kind of R version of parabolic induction, but sometimes not.
Okay,
Yes.
both cases.
Both cases, yeah. and everything in between. So far I wrote everything for GL2, but in fact this is really this is arbitrary. Yeah, you take G to be a connected reductive group. Yes.
And it has to have some property.
Theta has some property so that this thing controls the irreducibility. Yeah, so there's some genericity assumption. So I'm happy to write that. So theta generic. I'll write it like this. Theta generic. And that terminology will come up in a moment as well. Okay, so we have this situation.
So here you're working with Perverse sheaves and this
Yeah.
this group over.
Yes. Yes.
But
and-
it still is a variety over Q bar.
Yes. It's an algebraic group. Yeah, it's no longer a reductive group. It's kind of like a reductive group with this like fat unipotent part, like adhered to it. Yeah. Okay, so let me 5 here. Okay, my last page. So oh yeah, and I didn't say who this is due to. This last part, this intermediate extension again determines this. This is joint work with Roman Bezrukavnikov. Okay. So
Does this last part hold in the mixed characteristic case?
yes.
Good.
Okay. So recall. So do I have 10 more minutes? 5-ish? Okay. Okay. So what I would like to do is to revisit the so recall when we took for parabolic induction, the character formula of this looked like this. Oh. HGH. Okay. So what I want to do is to write down for you how to translate a formula like this into algebraic geometry land. So the passage is via this sheaves to functions correspondence. What sheaves to functions correspondence allows you to do basically is to model things in algebraic geometry, what you might do for an explicit function. And so natural things that you might do to a function correspond to natural things that you might do on the algebraic geometry side. For example, if you pull back a function, you'll do a pullback on the algebraic geometry side. If you average a function over something, that corresponds to a push forward on algebraic geometry side. And the fact that you can do these two things means that there's lots of interesting operators on functions that you can now translate to algebro-geometric terms. For example, Fourier transform. Everyone loves Fourier transform. There's a version on the sheaf side. Convolution, there's a version on the sheaf side. And so let's do that in this particular situation. So what will it look like? Well, over here I have an averaging, which means that I want to push forward something. So where will I push it to? Oh yeah, so I want to push forward something, and where will I push it to? Well, I'm taking values over here, so I'll push it to G. And what does this average over? This average should be over whatever the fibers are. So I want to cook up something up here such that the fibers of this projection map is exactly equal to this. Well, there's an easy way to do this, which is just like to force it to be true. I take all G comma HB inside G times G mod B, satisfying exactly this condition. And take this map and I map to G. Okay, so that takes care of this. What am I going to average? I'm going to average this thing. So now I have to translate this. This is a pullback because I have this composition over here. And so what I can do is push this t or map this t where I take this here and I map it to the projection of H inverse. This is F. So something that's very closely related to this second statement over here, this intermediate extension, is what happens if you study this. Oh, look, let me say, so sheaf version of parabolic induction of theta is given by F, we call that L theta. L theta is the L theta we saw already. Note. This is the intermediate extension of this L theta plus W L theta. So let me finish up by one more word. Okay. So thinking about this p-adic group thing, you kind of not only want to understand this situation, but also the situation where GL2FP is replaced by this flattened version of GL2FP, which is this GR. Now, what one can observe is that, in fact, each of these objects in this diagram here have R versions, have flattened versions. And so you can very well take this here, just put an R everywhere. And this is like working in a congruent subgroup where, like, instead of mod P, you're taking like mod P to the 1. So, in this direction, Lusztig made a conjecture around 2005 and said that in this R positive situation, and theta is generic, just this same generic that I told over here, then in fact, this resulting geometric version of parabolic induction is a simple perverse sheaf. In that same paper where he posed this, he proved it to be true for R is equal to 1 for G equals to GL2 maybe? I don't exactly remember. Okay, so let me erase this. I don't exactly remember what it is. And the reason I don't remember is that in 2016, he proved a more general result, which is for G arbitrary, this conjecture holds for R is equal to 1 and R is equal to 3. And so you'll notice that 2 is not there. And yeah, so for 2, the technique just didn't work. It proved something approaching, but it wasn't enough. So the theorem I want to end on, and then is a resolution to this. So this is that how we see something? Lower. The function associated to this gene is the character of the desired representation. In other words, this commutative square that I wrote down before also works for R positive. So I'll end here and thank you.
Questions for a speaker?
I have one question. Lusztig has classified for, if we're back to the finite case, the finite, that group over finite field, is classified these irreducible representation. And you can look, basically the character for semi-simple are easier than unipotent delta. If you look what it means in this classification to have basically you have the list of character with some kind of combinatoric stuff. And what it means, you're saying semi-simple basically gives you the identity with character. If you look what it means for the classification.
Okay, so two things here is the story so far is I always take my G and I restrict to the regular semisimple locus.
Yeah.
The notion of semisimple here is not the same as the notion of semisimple that you say in the classification, because the notion of semisimple and unipotent in the classification that you mentioned is parameterizing the representation. So it's not about the input of the character function. So the story that I've painted over here is purely in the semi-simple, are exactly about the representations that are parameterized by regular semi-simple elements of the dual in Lusztig's classification. So on the one hand, this is most of the situation, but on the other hand, it's kind of the easier part. And it's because it's the easier part that we can say strong theorems of the form that we only need to know what happens on the regular semisimple locus in order to recover everything. In general, for an arbitrary representation of G of FQ, this is not true. Does that? Yeah.
So what's the relation between the theorems here? Because the intermediate extension is like a simple Perverse sheaf. Is that how it's proven this, or
If you take the intermediate extension of this thing, you get a simple Perverse sheaf. But it's pretty hard to compute what that thing is. And so instead you might say, okay, well, I'll construct this other thing. This thing I can prove is a simple Perverse sheaf. I can calculate its restriction to the regular semisimple locus. It equals to that local system. So they're the same. Yeah. So, like, why would you want this now? This allows you to compare it to, like, I mean, if you just take this thing and you take its associated function, you actually don't know that it's the character of a representation. You just know it's a class function. And it's quite non-trivial to try to figure out whether it's even possibly the character of a representation. And in order to do that, it's quite important that we have it in this form so that we can apply some analysis to it and see that actually it recovers the trace of it recovers the character of the positive depth version of W Lusztig convection. That is.
So the odd fact of this conjecture initially being proven for 1 and 3, but not 2, does your proof now like explain what was going on with why 2 was harder?
Yeah, it doesn't explain. Okay, so yeah, the proof is uniform for all R. Like from the perspective, what?
Sorry, I just said 2 is an odd prime.
Yeah, so so in my situation, it for all the even ones, okay, well, one step at a time. So said, does it illuminate why 2 is hard? So in some sense, the answer is no, because our approach is really works for all R simultaneously. It doesn't see that there's a complication depending on the parity of R. But for representation theoretic reasons, there is definitely a difference between what happens when R is odd and R is even. And this is actually a really, really long story, decades long story. And the summary is that suppose you're trying to write down a bunch of representations of p-adic groups. It turns out that when R is odd, it's easier than when R is even. When R is even, you have to do an additional step using something called the Veith-Heisenberg representation. And this additional step is the cause of a lot of parity phenomena. And so I think like in the end, that's what's happening. That's why it's going on, why 2 was difficult. However, our technique here does not see the difference between these parities.
One last question.
So how similar are the character tables of GL2 FP of T mod T to the R and GLT of Z mod T mod T to the R?
So this allows me to say the first, a big thing that I hid under the rug. So, I told you that basically all the irreducible representations of GL2 FP are of the form, like they're either come from this, they come from this star theta. The analogous statement is not true down here. The problem of figuring out what the full character table is for GR, I think is too hard. Like that problem is harder than figuring out what all the representations of p-adic groups are, for example. And so for me, since somehow my original motivation is over here, I'm sort of satisfied if I have enough representations over here in order to extract lots of interesting ones over here. But I am in no way claiming that I have an exhaustive list of the ones over here. And so it's quite different. Yeah.
But my idle question was more, so this might be a mess, this character table, but I'm
Yeah.
wondering how similar it is to the other one, which might be. I mean, like, for example, would it be reasonable to think that the dimensions of these reducible representations would be the same, or the number of conjugacy classes? You don't think so?
This one. Like
Yeah.
any representation of this pulls back to a representation here.
Right.
So it's like, I mean, a character table is a square thing. Like but I guess if you group it so that all the ones that came from this step 0 are at the top, then there's some slice of this the character table that's exactly what came from the earlier step.
No, but I'm asking between FP of T mod P to the R and GL2 of F Z mod P to the R.
Oh, my apologies. I totally misunderstood. Okay. Yeah, this is great question. So there is work on this. So one way to phrase this question is if you consider the group algebra for this one, so the ring version of this versus the ring version of this, are they isomorphic? And I think the answer is sometimes, but mostly no. Yeah. And so I can give you some references. I didn't know about it. Yeah, so it's quite interesting. It turns out that the answer is no. Yeah. I was, to be honest, I was really shocked by this. Yeah.
Okay, well, in the interest, we should stop in case people have to leave, but let's thank our speaker again.